Okay, great. We're ready to go.
Good. Then I can start?
Yes.
Okay, then good morning, everybody. I welcome you to this presentation, the frame of the StoRIES project. My name is Marcel Weil. Maybe just in the beginning, a short introduction from myself regarding my person. So I should click here. Okay, yeah, I'm working already for 25 years in the field of sustainability assessment with all the different methods and tools, especially a strong focus on all the LCA methodology, which are, of course, a traditional environmental life cycle assessment, but also life cycle costing or social LCA, or in the end, also the combination of all the different dimensions and then doing sustainability assessment. Yeah, so, and we have a strong focus on batteries, and that already for 15 years, but we also focus on other energy technologies in our group. That's then power to X, hydrogen, of course, biomass, and so on, and then also, of course, not only energy production or yeah, energy storage, but also sometimes also CO2 usage, CO2 storage, and such topics. Regarding my affiliation, my host institution is the ITAS Institute in Karlsruhe, Germany. That's the Institute for Technology Assessment and System Analysis. And so it's a quite interdisciplinary research unit. My chief, for instance, is a philosopher, and we have a lot of social scientists, political scientists, and others. And we belong more or less even to the kind of engineers, even if we are not really engineers. Yeah. Then I have a second affiliation at HIU, the Helmholtz Institute Ulm for Electrochemical Storage System, and therefore I have this strong focus, especially on energy storage system, especially post-lithium batteries, and that belongs even then to the Celeste cluster, the Center for Electrochemical Energy Storage, and here, it's more than batteries, then also hydrogen and other topics. Then I have even a third affiliation, that's the cluster of excellence for post-lithium battery systems. Here I'm a PI and also executive board member. And just recently we get now the positive news that we have a new funding period for the next 7 years for Polis 2. That is, of course, quite amazing. Together, actually, it's not only KIT, it's also together with the University of Ulm and the Gießen University. Okay, and then we also belong to the Helmholtz Society, and there's also a network of excellence for post-lithium battery systems. And then even to have then in the end also the bigger picture, then here we also looking on the full energy system in the future and how it could looks like. Yeah? And then of course batteries is maybe one option and one important item for the future, but of course there are much more. We are quite active in international flagships or activities. That's, for instance, the Battery 2030 Plus in Europe. Then the ERA, there are different ERAs, European Energy Research Alliance. We are active in the energy storage system, and here we're heading the subgroup of techno-economics and sustainability. Then also for VDE in Germany, Batteries Europe with BEPA, we are here, I'm personally here heading the group of the Task Force Sustainability. Then we're also involved in the carbon footprint regulation of the EU and supported all these activities. And now, rather recently, now we are also invited to support the strategic European energy technology plan, the so-called SET plan. Yeah? And here we are responsible for the topic energy storage. Yeah, just now to coming closer to the topic. Yeah, of course, we are in the middle, hopefully, of the energy and mobility transition. And if you want to solve our big problems globally, That's not only global warming, of course. Then, of course, we have to stop the use of fossil fuels in all sectors. And that's not only driving cars. It's, of course, then also on industry level, on the commercial customer level, the household level. And that's, of course, also the mobility is a big fraction. And here, on one side, we have to deal, of course, with the whole society and to really bring this developments forwards, and have to address, beside technology developments, also the complete society, looking for the interaction with the society, really to solve the environmental problems, to find a techno-economic pathway which is possible in the end. And hopefully this is all then supported also by politicians which has a clear vision and a clear understanding what is now what we have to do at present, to solve the big challenging problems at present. That's at least on EU level. There is now here a certain awareness, and the awareness is even in such a way that they're saying, oh, look, batteries are really a key item, for all the developments in the future. And therefore, maybe that was maybe also the reason that at least the battery sector is now one of the first sector that you have a battery passport. You have special European regulation for batteries here. They are absolutely at the forefront. For the other technologies, such things do not exist. So you see, at least on the EU side, they're really aware that battery technology is an important topic, and we have to focus on that. And for that, we need also some regulations and framing conditions. Otherwise, maybe this development maybe goes not in the right and hopefully more sustainable direction. So, and that are maybe, there are a lot of investigation. That is just from McKinsey, but you find a lot of such future perspectives, how maybe the demand for batteries will develop in the future, in the close future. You find even numbers for 2050 nowadays. So, and but one thing which was clearly mentioned always in all the studies, well, the major demand of batteries coming from the mobility sector. That means for electric cars, but also especially from electric cars, we have to say, but of course also public transport, maybe two-wheelers and such things. Actually, consumer electronics, which are our daily items which we use, they are of course important, but the batteries are rather small, and therefore there's not a huge impact. So that is actually the perspective of many of the studies. So we have a little bit a different perspective from that. We say, of course, mobility will be a major driver for the demand of batteries usage, but there will be also a tremendous demand on batteries in the field of stationary energy storage. And that is not a development which is restricted to Europe. You see it clearly now here in this nice graph. If you see it also in the numbers for Asia, especially China, US, there is a big demand already nowadays, and the perspectives here are there will be even a strong increase in demand in stationary storage. And that actually is also what we believe. And there will be hopefully also a publication from our side quite soon with that. So we will see. So of course, mobility is important, but our message is, don't forget the stationary part, because that will be also play an important role in the future. Okay, and then just for the stationary part, of course, hydro energy storage, pumped hydro storage, it's still a big player. In the past, it was the biggest player at all, but it's now the most recent data which I could find from 2024. And now this part of non-hydro energy storage with batteries, especially batteries, is now a high percentage. And look in detail on the right side, which technology is managing this big increase in the past, then you really see, oh, it's lithium ion, and all the others, which are maybe sometimes are mentioned in news, whatever, are not so important. The compressed air, it's rather small flywheels. Supercapacitors, of course, a very interesting technology, but at least in the moment, not a big player. Flow batteries, vanadium redox flow batteries, interesting, but not a big player. The big player is lithium-ion batteries. Okay, and that is then also for both sectors, mobility sector and stationary storage. Lithium-ion batteries are the big players. All the others not so dominant or not have a big contribution. So, and then if you look more in detail on the right side, especially for the future, it's seen that lithium iron phosphate is a big player, and all the NMC systems, which contains nickel, manganese, and cobalt. Okay, and if you are maybe an expert in batteries, then of course you know, all the different lithium-ion batteries. LFP is mentioned; it's the blue one here on the right side, and NMC, that's in the bottom line, the red one. That all the different lithium-ion battery technologies has advantages and disadvantages, and then you always has to find maybe the right lithium-ion battery technology for the right application, especially for, of course, if you think about your smartphone, then you need a totally different battery. You really need, with a small volume, a high performance battery. And maybe for stationary applications, the volume and the weight is not so important. Therefore, you can go maybe rather for heavy lithium-ion batteries with maybe lower energy density, for instance, like LFP. And so, depending on your application field which you consider, you will select the most suitable, which fits also to your economic window, of course. And then if you maybe also follow all the news which are in online media or newspapers, then you always recognize, there's a lot of announcements, and unfortunately, quite often the announcements come from Asia, especially China, with all the dominant companies like CATL or BYD and all the others. And so they always push the market forwards and saying, oh, well, look, here we have the highest energy density, the highest lifetime, now super fast charging, and so on. This big news are always, I would say, nearly always coming from Asia, not from Europe and not from the States. Nevertheless, we are convinced, that the lithium-ion battery technology, that is really a disruptive technology, because otherwise, and it's just why it's so important, and why there was then even a Nobel Prize for the lithium-ion battery in the past, because otherwise your smartphone would look like that, or your electric car would look like that, but potentially with a trailer in the back with the battery, with a lead acid battery, or your laptop may be with a bigger screen, but with the battery on the side. Therefore, if lithium-ion battery was a game changer for all the developments which we see today, that's really a disruptive technology. So a lot of people always promise, there is maybe a disruptive technology. Well, lithium-ion is really a disruptive technology, and push all the developments in different sectors forwards. And if you look around, what you are using, your smartphones, your sensors in your house, so there's a lot of lithium-ion batteries already in place, rechargeable, sometimes also not rechargeable, but then nevertheless lithium-ion batteries with high performance. So it looks like there is a bright future of batteries globally and also in Europe. Even if maybe some activities failed, like Northvolt, which is still here in this map, there's a lot of plannings, and some are already in place. So there are a lot of plannings for big cell production in Europe. We, for instance, cooperate with one company in South Italy, it's FAM, and they also have industrial-like production. So there are some activities, of course, much more activities in Asia, especially on the industrial scale. But even the Asian companies invest here in Europe or in the States and produce also batteries in all the different countries. So a bright future, as I said. And then there are coming people like us. I'm sorry about that. And then we are saying, potentially the lithium-ion batteries are not so sustainable, or at least we have a question mark regarding sustainability. And why? Well, of course, as you know, they rely on so-called critical regarding the EU definition, critical and vulnerable. That means me depending to a high percentage from imports in Europe. Yeah, that is even also true for the states in a certain extent, but especially for EU, we depend quite often to a high percentage on imports, and imports especially from so-called not political stable countries or countries which are strong influence from Asia. Yeah? And the metals which are considered, of course, as you know, cobalt, lithium, nickel, copper. Copper sometimes it's underestimated the role, but also then phosphorus as a critical raw material, and a natural graphite and also synthetic graphite, also now belonging to the so-called critical raw materials. And so we have to change here something, because otherwise the people, the countries which export such critical raw materials, yeah, have a yeah, can steer any development or even stop any development in other countries just by blocking then the export of such materials. And that is a big danger, and the EU and of course all the other countries try to solve this issue, that we're looking for some more regional available resources or to replace resources. The next point is that the production cost and the life cycle cost are still too high. Then we have, of course, huge environmental and social impacts of the production of batteries, and that is of course also including toxicity aspects. And one of the, I would say at least, rather new topic which is in the focus at present is PFAS, yeah, because PFAS, you have a lot of PFAS on one side in internal components of batteries like the binder, and sometimes then even on outside components like sealings, whatever of batteries, there's also PFAS included, and that is, in the moment at least, on a political level, a really big issue. Then we have then, yeah, the technology performance needs further to improve, because if you reach a higher lifetime, a higher energy density, then it's quite good actually if we conduct a life cycle assessment. So it's really promising. But we're always also saying, yeah, the big points are, of course, energy density and life cycle time, but you also have to focus then on internal resistance, yeah, because that is then also important, how much losses you have, and losses means also heat production, and you have to deal with the heat, especially, yeah, to cool, and maybe active cooling, which is also quite bad, and then also the self-discharge, especially if not use it every time, and you maybe you that the system sometimes not in, yeah, not working, it's not used, and therefore then you have then issues with self-discharge. So that is also important indicators which we have to focus on. Yeah, and then recycling. Yeah, recycling is a big topic, and it's still too complex. Yeah, you can easily recycle batteries, but it's really a complex process. In the end, it's really energy intensive and materials intensive. So sometimes we have to think about how we can improve the recycling at present. We have maybe focus on that later. And then last but not least, then there are also safety issues. And I'll maybe in the news we sometimes find informations, there are some batteries are burning by bicycles, laptops, electric vehicles, yeah, cars, and so on. Yeah. Then the safety issues are not only then during the use phase, but also then are quite important in the second use and recycling, because a recycler has to deal with the batteries, and then if they are start with a so-called thermal runaway, then also sometimes also in such recycling companies there's a big fire caused by the lithium-ion batteries. So yeah, not so sustainable, and that actually is the reason in the end, yeah, that we are focusing on post-lithium batteries. Yeah? And then you're looking for the full periodic table and look, which systems are promising, and that's of course sodium. That is in the moment a really interesting system, which is really close to industrial production or is already in industrial production even. Then potassium, magnesium, calcium, aluminium, zinc, chloride, and even more. And that is under investigations at KIT, within Polis, within Helmholtz Institute Ulm, but of course globally. Yeah, there are big players and even industry companies with big research groups. So that's a big development towards this so-called post-lithium batteries, which is say at least one major advantage is that we use abundant material in contrast to so-called critical raw materials like lithium, cobalt, nickel, copper, and so on. Here, it was my try, I would say. So please not take this graph so serious. But the question is always, you have an idea about the so-called technology readiness level of the different systems. And sometimes it's really difficult to estimate because there's always a big discrepancy between what you hear in news, because then you always have the feeling, everything is solved. But if we then talk with technology developers, they only talk about problems. So, and then we have always this two elements, and that's a bit crazy. On one side, the news says, now we have a new system running very well with high performance, and everything is solved. And then the others, the real people which are working at the base saying, okay, maybe they have a running system, but maybe they still have the problem of this, that, and so crazy. So that means here it's only my first try to say, okay, what is the different TRL level? And lithium is of course clear. Maybe for this graph, it's a very special graph. Normally the TRL level is only from 1 to 9. And this one is from a colleague, Uderiko Ulyssi. He established a new TRL level 10 and say, okay, there's even something which is technology is really in place, and there's no issue and no problems further than widespread adoption, no recall. So, but normally it's 1 to 9, and in this case he maybe because it was a Nature publication, then you always have to present some new stuff. And then he said, well, let's include also a TRL 10, so it's nice. And then, okay, lithium is of course clearly 9 to 10. Sodium, as I said, close to industrial application. There are already some small electric vehicles which are powered by a sodium battery. Then the others with potassium, magnesium, calcium, aluminum, zinc. They are really interesting, but sometimes difficult to estimate where they are. They are sometimes, depending on the chemistry, really early TRL. Some are maybe already more advanced. So it's also here, it's not a clear answer. And then, of course, also the big topics of solid state batteries, metal air batteries, metal batteries. There's a lot of big bunch of different options. They are still in early TRL. So they are interesting, but of course far away in the moment from industrial application. At least if there would be not a tremendous breakthrough. You never know. If you maybe solve one big hurdle, like especially for maybe metal air batteries, all the problem with maybe some side effects, then of course you have very fast maybe industrial applications. So that was just my try to have a certain estimation of the different TRL levels. But we will focus in this presentation mainly on lithium and sodium batteries, so, and magnesium actually too. Okay, now we're coming to the topic sustainability. And if we think about sustainability, then we're not only looking for the production, we're really looking on the different raw materials, the design phase, quite important, the production itself, of course, the use phase, the different use phase, because there will be also in the future not the one battery which solves everything. Maybe there will be a dominant one, but there will be still other batteries maybe which really fits to a nice niche application. So also the use phase, and we have to assess the different battery types always in respect to their very specific application case. Then maybe the potential second use, third use of the batteries is a huge topic. If it's really possible, we will see in the future. And then, of course, last but not least, recycling, or hopefully recycling. But as I said, recycling is solved so far. And then, again, sustainability, but what different perspectives or methodologies I can address the topic of sustainability, which of course on one side have traditionally, I would say, just the three dimension of economy, ecology, and social or societal aspects. And And then if we address that, at least in the upper part from a rather quantitative assessment, then we have the traditional MFA, the material flow analysis, or also sometimes dynamic material flow analysis, especially important if you try to understand if there are maybe some critical raw materials, or what could be then the full loop of such materials in the full global system, material flow system. Then the full family of life cycle sustainability assessment with the different LCA methodologies, with the environmental life cycle assessment, the life cycle costing, and the social life cycle assessment. And then bring everything together, maybe potentially with so-called methods and tools in the way of multi-criteria decision analysis, MCDA. Here on one side, we can bring together different dimensions, different indicators, even sometimes quantitative indicators, qualitative indicators. And one of the MCDA big advantages then also to bring maybe use this kind of method and tool to bring also societal stakeholder into this evaluation. Then what is more important? Yeah, is now the performance more important? Is more the environmental aspects more important? Are the social aspects more important? So bring also this kind of assessment closer to society reflection. And then in the lower part, then especially things which are rather qualitative or even just overarching, like the sustainability concept, which was developed even at ITAS, then maybe social analysis, societal analysis, especially maybe also regarding acceptance issues, then the whole field of TA, technology assessment, also maybe with some maybe rather exotic topics like ethics, yeah, from our philosopher, or sufficiency, yeah, that maybe, yeah, do we need everybody an electric vehicle, or maybe we share in the future an electric vehicle? Such questions, and maybe do we need in any case an electric vehicle, or we all should use public transport? Such kind of questions. So just that you have understanding, there are different ways to focus on the big topic of sustainability, and even beyond. That's even just a selection. Okay, let's start. Now focusing on sustainability, raw materials, and maybe the topic of recycling. And here that's actually a quite old graph then, because it's everything when we started already, I don't know, 15, 20 years ago with this topic. And then always the question was, okay, there are a bunch of different metals which I have to use for the production of batteries for different applications, for different scenarios. And then the question is always, do we have enough resources? Local or global, or do we have then maybe some conflicts, or maybe we should support more the establishment of more mines and so on. And then of course also how we get back all these materials in the recycling loop to the usage, hopefully then in a closed loop recycling to bring it back to the battery sector, or sometimes of course also in open loop, that maybe some materials maybe can be used even in other sectors, for instance for glass production or whatever. Okay, we did, as I said, a lot of different investigations in the past, and maybe just to focus on one here. It's also a rather old, from 2018, and then we focused here on the mobility sector. And mobility, of course, is then especially the focus, what are the effects of electric vehicle, And here we have a lot of changes actually at present time, but we will focus also on that. And here a graph even from 2012, but just that you understand what is behind the MFA model, the material MFA model. And it's from 2012. It's already 13, 14 years old. So, but the idea behind is clear, that we're looking on one side, on the left side, then where are the resources, the different resources. We have the salt deposit, the brines, especially in South America. Then we have spodumene, maybe spodumene especially in, for instance, Norway, Asia, or Australia. Then we have even lepidolite or pentaltite, or even some glimmer with lithium, and but they are not so important in the past and also nowadays. Yeah, and then of course the production and the usage. And in the past there was the big production of the usage of lithium in the glass and ceramic, and batteries was just coming up. This changed dramatically, of course. Now it's batteries is the biggest sector by far. I would say dominate by 80%, and all the others like lubricants or alloys are not any longer so important as the application of lithium. And then also see what happens then after the usage of the metals or the materials, and then what end of life. It's maybe a recycling. Do we have dissipative losses? Yeah, that just they end up in the environment and no way to bring it back. Or there's maybe even the potential to have really a closed loop recycling, or at least an open loop recycling. Yeah, based on such basic understanding of a MFA, then we develop a dynamic MFA model, and it look at here on the right side, and we focus not only on lithium, then also of course all the other materials: cobalt, nickel, manganese, aluminum, copper, iron, phosphate, and even graphite. And then you see the different parameters which are maybe change over time, of course, like the global population, how much cars we have per capita, the vehicle lifetime, the battery lifetime, the market share of different vehicle types, and then of course the different metal content in the different battery types. Also that was the beginning, quite dynamic model, but also rather simple one. And at this time, it was really difficult to estimate how the parameter change over time with the population, but especially also with the batteries. How big are the batteries in the electric vehicle? And here we have full electric vehicle, plug-in, hybrid, and fuel cell electric vehicles. So we even include fuel cell electric vehicle. And then we estimated the battery size, and you already see nowadays you would laugh about that, because if you see even a middle class car, they have already much bigger batteries. So that was that was at this time rather conservative assumption, but that is the development is totally different. We'll see it later. And here then how it develops then over time, and then the vehicle life and battery lifetime and so on. Then that was regarding the these scenarios, and we called it low LFP, as a low lithium iron phosphate battery ratio. That means all the other technologies, battery technologies, dominates, and then medium and high LFP, that means is dominated by 75% by LFP, and the others then cope with the rest. And then this time, that's maybe just the funny part, at this time, then I received even calls from my colleagues which doing real battery research. And then they called me and say, okay, now we know you may be an expert for sustainability. For batteries, you have no idea, because LFP will never enter the car sectors. That was 2018. And that was the experts of battery. And now it's totally changed. Now the market leaders like BYD, CATL, Tesla, they use, of course, LFP. They had, of course, also some developments, not only on cell level, also on pack level. So, but nonetheless, as you see how fast this changed within a short time of 7 years. Even such scenarios, which was just a scenario then, that was then for experts at this time, oh, no, that will never happen. And then nowadays, it's the state of the art. Just a fun fact on the side. So coming to cobalt, as you know, and you know it from all the news, well, we have the big problem that the cobalt is especially situated in Congo. Congo is a very political unstable country, and highly influenced by all nations which try to have access to the resources of Congo. Then, of course, there are also some other players, Zambia, which they try to push in the moment forward, but also Australia as a big country with a lot of outback, which you can start mines everywhere, and they have a lot of resources. And yeah, so, but nevertheless, it's critical because Congo, yeah, is in the center, and therefore we highly depends on Congo and maybe the countries which influence Congo. Yeah? Therefore, cobalt is quite critical. So yeah, let's see how maybe then this affects then the scenario. On the right side here, you see the reserves and the resources. The reserve part of the resources is the part which you can mine in an economic manner nowadays. But this change also over time. And sometimes even the value for resources change over time, because if you look for new mines, maybe you are very successful and find maybe new deposits. So reserves and resources are estimations about the present knowledge, how much is available globally, but in the future maybe this will change. And sometimes change even in the negative because you overstressed it already. Sometimes, quite often, even it's more than rather positive that you find new deposits and therefore the values increase. But nevertheless, if you see even for the three different scenarios, and then we have then the low LFP and the middle and the high LFP, combined with different recycling rates, yeah, with the estimations are if we would recycle 50% of the cobalt, with its not really realistic, but because cobalt is quite expensive, so all recyclers try to recycle as much as possible of the cobalt. And so the other scenario with 90% recycling rate, it's rather realistic, and some even are higher, yeah, than 95 or even 98 of cobalt. So yeah, but that was the scenario, and you see in all the different scenarios that at least for most cases, even in the most optimistic ones, you would consume more or less the global available reserves, or a significant fracture of the available resources. So, and that is, of course, and that is only for the batteries. Yeah, of course, you need also cobalt for other sectors. That's only for the mobility sector and for batteries. So it would be stress the reserves and resources significantly. So therefore, we need a solution here. Yeah, and yeah, LFP is of course already part of the solution. Coming to lithium, lithium here you see it's much better distributed globally, and therefore not so critical. Even in Germany now, they try to mine some lithium on one side from minerals and close to Freiberg. But even here in my region, the Rhine Valley, they think about, or not they think about, they do it already, to use geothermal plants also to use it, yeah, to get out the lithium from the deep groundwater, I would say. Yeah? So, and yeah, and therefore that is supported by EU. That we of course also have potentially some own lithium sources. One activity it's really in Europe. It's in Portugal, and also some East European countries. There are some ongoing activities. But of course, the big players in the moment are Australia, interestingly, and but also South America is one of the biggest producers, and China, of course. Yeah, let's have a look here for the different scenario with again with different recycling rates and the three different scenarios, basic scenarios with low LFP, middle LFP, and high LFP, and also in this case only for car e-mobility, you see that in all the scenarios you even overstress the reserves, or you would at least consume completely the reserves or high parts of the resources. And now then when we did, hopefully in the next slide, then also estimation what would happen if we also would replace all diesel engines in public transport of buses with yeah, battery-driven buses. Yeah, it's here. And you can see only, yeah, and we only looked here for the high LFP scenario because LFP is quite suitable for electric buses. And you see, even if we only go for the public transport globally, even that would consume a lot of the known reserves of lithium. So that is really critical. That was already, yeah, as I said, investigations in the past, and that was then, of course, the starting point in a certain way to say, oh, we have to we have to find a solution, and lithium is maybe interesting and have good performance, but we also have to find maybe systems which run without lithium, but especially, of course, without cobalt and nickel, for instance. For lithium, we also have to say, yeah, there's a tremendous development from the past to today. The big players, as I said, Australia, quite interesting because they have at least not so much known reserves, but they use it very intensively and they always find new deposits. Then Chile, China, and all the others, they extend the production significantly. The present problem is actually that the lithium price is really low at present, and that is of course quite bad for invest in new lithium mines. But we should of course invest in a certain extent in lithium mines because lithium batteries will play a dominant role in the future still, So for the next 10 years, I think lithium battery technology is the key player, and therefore there should be, of course, some developments that beside the price, which is at present low, there should maybe some other incentives that the people invest in lithium mines, because this should be the way to go, at least from a resource perspective. If you go not from the environmental perspective or social perspective, then of course there are tremendous impacts. You also have to deal with that and find maybe a solution for that. So of course, that is of course there are always different things and goal conflicts which you have maybe to combine in such a way that it's least not super critical. Then with all the calculations which are showed only for cobalt and lithium, not for the other metals, just due to the time restrictions, then of course we could say, okay, but all the sensitive parameter could change in the future. Maybe the battery lifetime increases, and therefore then in all the different cases, then also resource demand would decrease. And for instance, if the share of SOEs would also decrease, then of course then you use less battery for smaller cars, and then you would decrease the resource demand in the scenarios. But we also have to say, well, the opposite is true. If we increase the usage of SOE-sized cars, then of course there would be even a tremendous resource demand in the future. There would even more increase than we estimated. And the problem is, in fact, that we all should use such small cars. The bottom line in the green circle, we should use such cars. And what happens that we use, middle class, it's maybe would be still okay, but then we use trucks, SOEs, and that beyond even sports cars and so on. And they have a high demand on one side on big batteries and sometimes even on high performance batteries. And if you look about especially on high performance batteries, then you have to go for nickel cobalt systems for high performance, and LFP are rather than for others very suitable. So crazy enough. And you see here in the numbers, and you see, it was a strong increase already in the past, but the most recent numbers, 2024, we have already 45% of the new cars are SOEs. And that is, of course, a totally unsustainable pathway, which is, customer driven, society driven. So crazy. If we talk about, we need more sustainable batteries, it's nice. But in the end, the customers, the market decide that we go in a totally unsustainable pathway. And for this, of course, we need also a solution and maybe a trend, different trend, because that is, of course, not the right way in the moment we go. Now, coming more and more closer to the real battery topic, and for us especially, it's quite important that we influence the design of a new battery, because the design in the end determines everything. It determines later maybe how easy the production is going, or it determines how good they perform in the use phase. It determines if they are capable maybe to go for a second or third use phase. And in the end also determines recycling. And the EU is already talking about design for recycling, because if you develop a new technology today, you can't wait until 10, 15 years, and then there's a big waste problem. And then the people say, well, maybe the battery or any technology is difficult to recycle, and then we have to deal with that. So not this end of pipe thinking, so really influence the technology already nowadays, that maybe there are easy ways to improve the recyclability, which in the end pays off in 15 years if then the battery is ready for recycling after the use phase. So design for us quite important. Therefore, we are strong cooperations with companies, with the technical developers to influence, hopefully, the design in the right way, and also then to deal with prototypes. And we did it, in a long tradition. We published the first LCAs of sodium-ion batteries. Then we have the first cost assessment of sodium batteries, which is very highly cited, the most cited publications in my case. Then we had also the first LCA on saltwater batteries. We will focus on that later. The first LCA of magnesium batteries, and even a prospective LCA for sodium batteries. And now with colleagues of Japan, it's already published, the first LCA of potassium, in this case, was not calcium, potassium battery. So totally interesting that this is a long-term project, and it's really, you need the trust to cooperate with different technology developers, that you receive data from them, and then maybe you can suggest some improvements, and maybe also say, what is promising, what's not promising, and and you see, with 2016 now, our first LCA for sodium battery is more or less 10 years old, and so nowadays sodium is close to market introduction, so it's quite nice development. So, and if we talk about sustainability, of course, we normally try to focus always on the different dimensions. Sometimes it's not possible. Sometimes in early TRLs, just maybe with a certain indicator set, because a full LCA is maybe then too much. It's not possible in this early phase, and makes no sense in the end. And though, we try always to address the different dimensions or even to combine it, but we have a strong focus classically on life cycle assessment, focus on environmental aspects. If we talk about LCA, then of course traditionally the full life cycle here, if you think about electric car, whatever, then you need raw materials, you have to produce the car, then hopefully you use it in an efficient way, or in an efficient and sustainable way. Then hopefully then a second use of the battery, or then the reuse, remanufacturing, or last but not least recycling, and bring it back to the value streams. And if we talk about the LCA, life cycle assessment, it's not a new methodology. The ISO standard 4040 is from 2006. The ISO standard 44 is was maybe then 2 years later. So it's an established methodology, and I will not go to too much details of LCA, because that would too much for this seminar. But if you're of course interested in this topic, you can maybe later also contact us. Just to have a rough understanding, there are maybe 4 important traditional steps in LCA with golden scope definitions, also functional unit. Inventory is then all the inputs and outputs of your considered technology with the system boundaries. And then on top, if you have all material flows with that are emissions and energy use and waste and products, then you're doing on the top an impact assessment. You estimate, okay, if I have all this, because all this materials flow of this product, of this system, of this technology in a big electric or in an energy system, then you can assess different levels of granularity. Then you put on the top here, you try to understand what are the potential environmental effects, and like global warming, acidification, resource use, and such things. And then in the end, you do the interpretation on all the different levels, on the MFA level, on the inventory, but also on the impact assessment. And sometimes it happens that you recognize, you have a result, but that is not suitable to your goal. And then you do not one LCA, maybe you do 50 LCA in an iterative way. On one side to find the right result to the actually question and also to improve your LCA, yeah, with all the uncertainties, especially in early TRL. And that is then maybe yeah, used for different different stakeholder of society, for political advice, for industry, for technology developers, strategic planning, and so on. So different ways to do it, yeah. Yeah, and that is rather now this life cycle inventory that I see. Yeah, okay, that is already said. We consider I have a system which is in the box. That is my technology, and then I look, what goes in, the raw materials, the energy, and then what comes out, and beside the product, maybe the co-product, the waste, and so on. And if I have all these material flows, then I ask, okay, now to consider what are maybe the climate change issue, the eutrophication, land use, and so on. Yeah, toxicity. Yeah, and that is always the process. Yeah, first it's based on material flows from caused by the technology itself or the system, and then you put on the top, try to understand what is the effect of that, or maybe compare different technologies. And that is then called the impact assessment method, and that is the third part here in this graph. And then just do it now for one very important impact category, and that is the global warming potential. That's GWP in kilogram CO2 equivalent. And then this measures not only, this considers not only CO2, but also besides CO2, which is carbon dioxide here with one, they also consider other material flows. And here's just a selection like methane, nitrogen on the different fluorocarbons, or maybe even sulfur hexafluoride. And you see, yeah, carbon dioxide has for the global warming potential an influence factor of 1. All the other technologies sometimes 14,000 times higher, or even in the case of sulfur hexafluoride, even 20,000 times higher than carbon dioxide. So if you have any technology which use this kind of gas, that would be tremendous for the LCA and the result. So you always have to prevent the really bad ones and maybe exchange them. And that actually also happens because this kind of substance are in the past used for cooling systems, and so they are replaced more or less in many technologies nowadays, and they're looking still also for other technologies, maybe in car for the air condition and so on, for alternatives to not to use such critical gases. Okay, now we are still for the prototype, and now we have the example here, the prototype of magnesium sulfur batteries. And this prototype was produced by Custom Cells. They are again back in production. It's the good news, actually. They was bankrupt recently, but now they are again back and manufacture. So in this case, this cell was not optimized. Of course, the casing was too big of the prototype. The separator was double folded. It was a little bit crazy. Too much electrolyte and so on. Yeah. And then we said, okay, we discussed with the technology developers, okay, of course, there are some restrictions to produce such a prototype, but how we could theoretically improve, to say at least this would be low-hanging fruits to improve the cell. Yeah? And then was, okay, reduce the pouch mass, because the pouch was not optimized at all. Yeah? There was too much pouch, and therefore then we reduce it from 45% weight to 3%, which is the average of a normal modern lithium-ion battery cell. And then in the second step, then we also said, okay, then reduce the separator share and also reduce the electrolyte to a normal level, which is necessary that the cell would run just on the theoretical level. Okay, and then we have already the results. That is now in the moment a simplified indicator, the CAD. It's called CAD. It's beside the traditional impact assessment method. This is a very engineering-oriented indicator. It's called cumulative energy demand. It's just the energy indicator, and you see here already, okay, the normal not optimized cell, the first one, the first bar, as a high impact. If I would do the first reduction of the housing, that would already improve the the cell tremendously. And then if we are doing all the other optimization steps, then we really receive a significant reduction in the CAD and so also environment-related environmental impacts. So, and that we did also for the global warming potential, the indicator which you already know, and then very similar picture. Yeah, we have the not optimized cell, then the first reduction of the amount of the pouch cell, and then the improvement regarding electrolyte and separator. And you see a significant reduction already with this low-hanging fruits, which you say that is possible. Yeah, beside all the other technical hurdles of magnesium batteries, that is easy possible. And then we compare with average LFP batteries, and then at least that's saying not that is the truth, but it says, look, already with this estimation of potential improvement of the cells, we are in the range of a LFP cell, and that is promising. Beside all the problems with on a technical level, with maybe with lifetime, energy density, and so on, that is already promising. And then we can say, okay, we can focus further on this technology because it looks promising. If it would be 100 times higher than a LFP, then we have to really think about how we can reduce it in a realistic manner. So at least that are promising results, and say, okay, we have to solve still big hurdles of magnesium batteries, but that looks promising. So it's good. That was a good message, and we will see how that works further in the future. Then, of course, it's the question always where you produce this battery. Have a short look. It's already here. Where you produce this battery, and then depends, of course, which grid electricity is available. It's now coal power plants, or maybe nuclear power plants, or maybe there are a lot of renewables. And that we also did, and consider 3 different energy mixes in different countries. For instance, Switzerland, which is a rather green electricity mix, green in a certain way, well, with a lot of renewables and hydro. Then with a fraction of nuclear, which is at least CO2 friendly. Of course, nuclear has other disadvantages. And then only a small fraction of fossil, especially gas in this case. And then we have the EU, which is rather in the middle, still not the big player for renewables. Also, if the EU always thinking they are at the forefront, which is not true. And use a lot of fossils, a certain fraction of nuclear, which is of course not longer true for Germany, rather for France, and then also a certain fraction of hydro and renewables. And then in contrasting China, with a lot of fossil energy in the past, I have to say, and a certain amount of nuclear and hydro and renewables. And we really have to say, in China, this picture changes significantly from day to day. So they are the big player for renewables in China. So they have really a change in the mindset. And so that means quite soon, complete China has a more greener energy grid mix than Europe. So Europe has to set ambitious goals to keep in line with what they promise always, and especially that not in the end China, which we always saying from the past, they use of course a lot of fossil fuels, they have cheap coal and other stuff. This is the thing. So this is rather the old picture, China with a bad energy mix, which changes significantly nowadays. And you see, okay, if we produce this in Switzerland, it looks really nice because now we have here regarding GWP quite optimistic results. If you produce the same cell in China, there would be more nearly the impacts, the double impact regarding CO2. As I said, but this changed already significantly. NAU anywhere in the middle. So of course, then it's a question where you produce, and especially a lot of companies now going to East Europe because they got a lot of incentives to go to East Europe. But the energy mix in East Europe is quite often coal-based. So then of course, for the environment, that is not a good idea. Just the publications regarding that 2 graphs which I showed. Coming to the production, and maybe if you are in the topic of batteries, maybe you are much more familiar with the production of cells than I. But we did also some work in the past, and you see here the traditional way how to produce cells with the slurry mixing, the coating, the roll-to-roll pressing, the slitting and notching, winding, weld tapping, and then of course do you produce a round cell, cylindric cell, or do you produce a pouch cell? Of course, a big difference. Then the electrolyte injection, then in the end also the formation of the cell. So at least roughly is that. And that we investigated actually at KIT because we have all the different components. You see here one component from KIT. I think it's the two rolls which press on the electrode, the calendar, so-called calendering. And we investigated all the different steps of the production of a lithium-ion battery cell, on a rather sometimes laboratory scale. In this case, on the picture you see it's rather a pilot scale already, and then of course to understand better what that means, hopefully on industrial production scale. So we investigate, as I said, all the different steps, and that means really we enter the laboratories and measure for all the different steps the material consumptions, for instance, special gases, then the energy consumption for heat or other stuff, and also maybe estimate if there are potential emissions, maybe even measure emissions. So really, it was a lot of work to get primary data for all the different steps. And I have to say, primary data is always the only way to, in the end, produce reliable and robust LCAs or cost estimations. So therefore that is so important for us. Not easy, and sometimes we are not always welcome, if we ask for primary data, but that is the way to go to have in the end robust and reliable results. Okay, and then of course, sometimes they produce only 8 cells. That is, of course, the efficiency is really bad. But of course, if you would then also produce regarding the capacity, if you go really to the capacity of the line with 400 cells, then you reduce significantly the amount of impacts per cell or per kilowatt hour. And that is then especially important to understand. Here you see on the bottom part the global warming potential per watt-hour battery pack, and then on the left side then the production scale from lab, pilot to industrial. And the problem was in the past that there was a lot of promise from the industry how efficient they produce cells, and then nobody was aware, do they really offer reliable data, or they only produce how to say estimates, positive estimates, or how to say it political correct. And there was of course sometimes data which are really just rubbish. But here you see in the upper part some data from the past, and sometimes also more recent data here, for instance, with the cooperation of Northvolt, which not really exists nowadays. So I don't know about the data quality, but from our colleague Cordia, and he is always doing a good job. And you see, they have rather low global warming impacts on industrial scale. And here on the bottom line, then our investigation, which was partially on laboratory scale, then sometimes even on lab scale, and then we did a theoretical upscale. If we then doing for each step asking, okay, what are the effects for this production step if I would do upscale, increase the efficiency, especially then sometimes the speed from roll to roll, and maybe the heat usage if you try, maybe the electrodes and so on. And with this theoretical upscale, we managed at least to come really close already. That's the pilot scale numbers in the middle, really close to the industrial scale number. So on one side, then our model for the realistic data on lab scale are yeah, interesting to have at least then the chance to estimate then the potential effects on the lab scale or on the pilot scale, and then go even beyond on industrial scale. And then if we do this kind of investigations in the future for other technologies, then we have all the data for all the different steps. And for instance, for sodium battery, which is considered as a drop-in technology, we can just exchange then the very specific production steps for sodium to estimate the potential efforts on pilot and industrial scale in the future, and saying, then because in the end we want to compare lithium batteries on industrial scale with sodium cells on industrial scale, because otherwise the comparison would be, of course, not really fair. So this was a quite important work on one side to check even then the promised data from the industry, but also to calibrate our models in the end to be sure that also our models are working well and are close to a realistic data. Yeah, use phase scenario for batteries. Here in this case, we looked for stationary application, and I will not go too much in the different kind of applications. That's for stationary application. One, electricity time shift, arbitrage, the increase of photovoltaic self-consumption, the primary regulation and renewable support. And you see there's a significant difference in the energy to power ratio as an important indicator. And we compared not only traditional lithium-ion batteries, we also include then some exotic ones like vanadium redox flow batteries, but also very traditional lead acid battery. Yeah? So just to compare where they are and what are maybe the potential benefits or drawbacks for all the other technologies. On that are already the results regarding CO2. And you see on one side, the big uncertainty bars, that there is a lot of uncertainties in the model. Yeah, because that means, yeah, okay, it's not a clear message. Yeah, we always have to consider, okay, we have to deal with a lot of uncertainties, and sometimes the uncertainties are not only relates to new system, also to the old ones. Yeah. So, and you see here for the 4 different applications, the results, and then always for the different technologies with LFP and the NMC batteries, and then even vanadium redox flow, and the lead acid battery is then more rather on the right side. And then on the bottom line, you see the contribution of the different parts of the lifetime. Then the production or construction of the battery is this brown, I would say. The energy consumption during lifetime is then the gray, and the cell replacement, if they are at the end of the lifetime, of the cycle lifetime, would be then in blue. And in that, at least you see the different contributions from along the life cycle. Yeah, and so what you see, that's diverse depending on the application case, and maybe some tendency LFP already in this rather very early investigation. LFP performs always not too bad. Yeah, so that was already, we said, oh, LFP performs good. Yeah. Why not? And then we'll also recognize on one side, but the data for vanadium redox flow batteries really bad. The database for vanadium redox flow really bad. We have to improve it. Then we did even our own LCA for vanadium redox flow, and then really astonishing, really bad data quality and data availability for lead acid. Really. That's really crazy. Yeah. So in the past, everybody compared lithium batteries with lead acid batteries to show how good they are. But then we recognize, but all the old studies are actually rely on not good data for LFP, especially for Europe. Yeah. So crazy. Yeah. We will focus on that later. So. And that we did not only for CO2, then also for cost assessment, and very similar picture. Again, a lot of uncertainties, and then there's not a clear message for one or the other technologies. But again, LFP performs not too bad, and the others depends on the requirements in the considered application case. So we have to do always this kind of investigations only specific for the application case because the requirements are always different. So that is the message which is important here. Okay, I will not focus on the second use or third use phase. But if you're interested, there is also publication with a former colleague, which is coming from China. So maybe then you have a look here. Now we're coming to my big topic of recycling or refurbishment and such things, which is quite important. And as I said, recycling is really connected to design. And therefore, we try always to influence design to improve the recyclability in the future. Yeah? And that is the big thing, yeah? Because topics like, for instance, PFAS is a problem along the full lifetime, but especially then in the recycling. If you have PFAS, it is an issue. And if we could exchange, for instance, PFAS easily with other binder in the system, that would be already a big advantage. If not, or the new binder has not a good performance, then we have to really understand what that means over the lifetime. Therefore, we're not saying, well, this is a clear understanding. We still have to understand what that means if we would use a new binder, for instance, replacing toxic elements, which is critical for recycling, what that means in the use phase. Yeah? Because sometimes maybe there are then binders which are not good for the use phase. And then, of course, it's a question, or maybe the performance is so bad, then maybe it makes no sense to replace, at least not with this binder, this system. Good. Recyclability. Just this slide is a big topic, and in all the big flagships of EU. Here, for instance, battery 30 plus. Here with the roadmap, and there's just again an update of the roadmap. So maybe quite soon there will be a new version of the roadmap available. And here I'm again with Marcel Meus and others in charge for the topic of sustainability and recycling. Yeah, for battery recycling, we did also in the past some work, had some interaction with rather smaller companies in Europe, I have to say, with recycling, so that we really understand what is state of the art of recycling. Yeah, why is this important? And here maybe case one, and here we compared so-called aquatic hybrid battery. That was this Aqueon battery, the so-called saltwater battery is the first one, which was actually quite pushed in the US. Very interesting MIT prize and also investigation from Bill Gates and so on, and received a lot of money from government and industry and maybe from risk money. And then after a few years, it just burned, because there was bankrupt, and then the whole company was sold, and the patents also sold to China. And interestingly for us, I found this technology again back in Europe. If I go to a fair, there's a new company, and they produce the components. As I know it correctly, they produce the components in Asia, then they assembly in Austria, and therefore it's then a European technology, and then they go to fairs where the people which has their own house or whatever, and then they sell it as a green battery, still with good recyclability and so on. Yeah, we will see it later. Then the next is the vanadium redox flow battery in the middle. And here you see a photo from Finstal, Fraunhofer, and that is the biggest vanadium redox flow battery in Europe at present. And it's really impressive if you are in this hall and see all these big tanks with the electrolyte. So really impressive technology. And of course, here for this station application, maybe a quite good alternative. And then here just a very special lithium battery, LFP LTO batteries. And here we just check it for one application. It's just renewable support with some framing conditions regarding lifetime cycles per day and for this application. So And now we see then, that's maybe for the saltwater batteries, there's just this new icon here beside this saltwater batteries. That was even a cradle-to-cradle certificate because the recycling was so promising. Yeah? So it was really pushed for and say, well, that's a really green battery. Yeah. And now our results, and that is just, it's now not this global warming potential, it's the indicator for resource criticality. And we use two different indicators for resource criticality, and that is this you see the picture here that on the first bar it's the lithium-ion battery. In the middle there's the saltwater battery from Aqueon, and then on the right side in each graph, the vanadium redox flow battery. And you see, at least if you would not consider recycling, that the lithium-ion batteries performs excellent, ranks with the lowest impacts, followed by vanadium redox flow. And then due to the really bad performance during the use phase of this Aqueon battery, this is the worst technology. Instead, it's promised to be the greenest technology ever. Yeah. Okay, and then we considered with recycling, and then we have a change with the ranking order. Yeah. Then you see the best performing regarding both indicators for resource use. The vanadium redox flow battery, that performs best because you can easily recycling a vanadium redox flow battery after usage, because you have massive copper plates, which you can recycle very easy. You have pipes, which you can easily recycle. You have the electrolyte, vanadium containing electrolyte, which you can easily either even to reactivate or even to use in a different application. So, and therefore here, the message, okay, recycling is important, because if you not consider recycling and maybe then your recycling is not efficient, maybe other technologies could perform better in a certain application case just because they have a better, easy way to recycle the materials. So you not can rely on that your performance in the use phase is always overarching. You have also to ensure that end of life is quite that the recycling can take place efficiently, especially in comparison with other options of this technology. Then coming to a second example, and I think it's even the last example, the sodium battery and recycling. And you see sodium batteries just as a starter. Yeah, why is sodium battery so important as a topic? You see there are already estimates how the battery market for sodium will develop in the future, and this is only one of the estimates. There's even also other estimates from McKinsey or whatever, from other consulting companies. So they are thinking that there will be a tremendous demand and application of sodium batteries, especially in stationary applications, but also step by step also in automotive one. Yeah. So that is really interesting. Yeah. So really would be a really good development, because with the replacement of the lithium technology, at least in some applications, you can reduce, of course, the pressure on the resources. And why are sodium batteries so promising? They are basing, of course, on abundant sodium and hard carbon. Hard carbon you can even produce from biogenic waste. You use aluminium foil as current collector instead of copper in lithium-ion batteries, which is a big advantage because copper has a tremendous environmental impact. Also, aluminium is also not totally environmental friendly, but it's better than copper, and it's also not so critical as copper. Then the energy density is at least okay. LFP is still higher, and sometimes they have promised then a fast charging capability and also good cycle life. And there are even, if you follow the news, always new developments which they announce now, increasing lifetime and so on. And the big advantage also, it's a drop-in technology. That means even if you have maybe established a lithium production line with some smaller changes in the production line, you can easily also produce the a sodium battery, whatever that means. Yeah, if you talk with practitioners which are responsible for a production line, they always say, well, we have nevertheless to change a lot. Yeah, but yeah, at least, yeah, there is a way to change from lithium to sodium. Instead, if you go for maybe totally different technologies, you have to change maybe the production line completely. That is then then maybe something which would not happen so easily. And just to see, there are some of the big players, CATL, Faradio, and BYD. They looking on different sodium battery types, Prussian blue analogs, or layered oxides, layered metal oxides. That's one of the dominant technologies, or polyanionic, with all the different pros and cons. As you see, there are always then advantages, maybe for instance for Prussian blue, they have a lot of advantages, but they have one very complex to moisture sensitivity, and what they're not saying here, you have a cyanide issue. And this is of course, if you talk with society, and then you say you have a system which maybe if it burns, there could be then some cyanide. Or some combination with cyanide coming out of the system, it's of course not so good. On the other side, maybe they have other advantages. And if you say then look on the layered oxides, then the life cycle, at least in the past, was rather low, and the C rate was also low. There is a C rate also for charge and discharge. And so, depending on the application, maybe one or the other is more promising, and you still have to solve maybe some issues. Here you see just the market share, and you see here, dominant layered oxide technology, followed by Prussian blue and polyanionic, and so that is the market in the moment, and we will see how this maybe change then in the future. And there are a lot of activities ongoing in US and Europe. There's a lot of interest. Of course, not any longer Northvolt, but maybe then the following activity. So, but big interest. But the big players and the at the forefront, they are in Asia and especially in China with BYD, CATL. And Hina batteries, we will see it quite in the next slide, and so on. So the big player, SVolt even, and Japan, rather minor activity, and also minor activity in India. And why is so interesting? You see here there are already some testing. They already test some stationary batteries here from Faradion, a corporation here in Australia with Nayon Energy, or then here in Bivat from China. They already establish here big batteries, and you can already buy in I'm not sure Amazon, but maybe other platforms offer already sodium-ion batteries that you can buy for small household charge and discharge. So really interesting development. And then something which was not so expected was then also the usage of batteries, sodium batteries in cars. And that's Yak Motors and Hina Batteries. They have a cooperation, and they use already the sodium batteries and test them on a car level. And that is, of course, something which I say such things not takes place in Europe or US, it takes place in China, and they learn a lot, and we still have to learn a lot. So that therefore they are on the forefront, and we have to keep going, that we maybe reach the same level quite soon, because it's a really interesting technology. So we will see. And now CATL, as one of the big players, now even announced this Naxtra battery with a lot of performance indicators which are really promising. So it looks like, well, if they go this pathway, they could at least partially replace in some applications lithium technology by sodium batteries. So so the big points, they achieve high safety standards with the batteries. They have entered the automotive sector, which of course is much more complicated than stationary applications. So they managed to meet the high technical requirements in the automotive sector. That's amazing. They have close performance to LFP, and low temperature operation until minus 40 degrees, which is of course much better than other battery systems. And the mass production already takes place now, yeah, again in China. Good. And here was a nice cooperation with Volkswagen. They also look, of course, on future battery systems, and I supervise here also together with Helmut Ehrenberg and Werner Bauer, PhD, Jonas Sprengelmeier, and he compared here, for instance, the different lithium batteries with sodium batteries, and you see, and then even in different production location in Asia, Europe, and US, and you see at least independently from the technology, it makes sense at present to produce it in Europe, but I always say but because the electricity mix and the developments change totally in Asia and especially in China, they will be quite soon improving their performance and then have a greener energy mix than Europe. So then they will be the location for the production of greener batteries. Yeah. So that because in the moment it's just a snapshot at present. We still have a good energy mix in Europe, but China is coming and will overwhelm then the European energy grid mix quite soon. And yeah, that is the development. And we will see what happens in US. What we also see that still the sodium batteries, which are always on the right side of the different country perspective, they have the lower impact again for the global warming potential in comparison with the different sodium batteries. And that is mainly due to the lower gravimetric energy density, which are the blue dots. So you always see, for sodium, it's much lower in this case than the estimates for the different lithium technologies. So that is the main reason for this estimation. So the message is there's a snapshot again at present. There maybe has still disadvantage from the LCA perspective for GVP. Of course, you have to look then also for the other indicators. For resource use is a totally different picture, of course, because they use the non-critical raw materials. But at least here for GVP, it looks still that they have maybe not the best performance for certain application. But here's a cradle to gate perspective of only the production of the different systems. So then we did the other investigation here with, we also consider here the comparison of sodium and lithium batteries and different sodium chemistries, and then comparison with NMC and LFP batteries. And just have here a look here now on the results, and the focus is here now with recycling. Yeah, that means the first bar of all of this graph is only the production of the cell. Then the next bar is then what is the credit if you're doing mechanical recycling, and they get maybe the macroscopic materials from the mechanical recycling. That means the housing, the current collector, and such things. And then if I do in a sophisticated hydrometallurgical recycling, which kind of credit I receive if I recover in an optimistic scenario cobalt, nickel, lithium, manganese, and so on graphite. And then you see it. Yeah? And for NMC, that is the first column, then you see, there is some credit for mechanical recycling, and then there's a credit for the sophisticated hydro, and then you get a net value for which includes production and recycling. And that looks for NMC already quite promising. For LFP, it is a different picture. On one side, I have a higher impact due to the lower energy density. Then if I'm doing mechanical recycling, and then I need more battery, of course, for the same functional unit, for the same purpose. And then if I'm doing mechanical recycling, I receive a nice credit for the recovered macroscopic metals, current collector, housing, and so on. If I do then a sophisticated hydro step, just in the same way then for NMC, then I have a that is important. You receive a negative impact because you use a lot of energy, a lot of chemicals for this hydro step, but the value of your recycled materials, it's only lithium, iron, phosphorus, graphite, is so low, then that's even negative. So you would increase the impact by including a full recycling for LFP. And that actually also happens for sodium in some cases. So you see here now in yellow the comparison with the different sodium types. And you see on one side, again, very similar to the Volkswagen investigation, that here the bars for the production are higher in comparison to lithium NMC system on lithium LFP system. That is one thing. The other thing is if you do recycling, sometimes you receive positive credit, but sometimes in this, and especially in the second and the third case, or also in the fifth case, you then, if you do a sophisticated hydrometallurgical recycling step very similar to NMC, you would have a negative impact because, again, you use a lot of energy, a lot of materials like chemicals to produce the materials for the recycling. And the value of the materials which you for recycling are rather low. Okay, so recycling is quite important. You see here now, beside the global warming potential, also in resource indicator ADP, and you see, of course, for sodium performs much better than the lithium counterparts regarding resource use, but also here recycling is interesting to look in detail what are the effects for positive or negative credit. Okay, now we are very close to the end. Just here regarding the value in materials, again, if you think about the recycling of a LFP or an NMC battery, then you have, that was the measures which I tried to explain before, you have a high value in the material. For the different sodium batteries, independently from the system, CATL, Faradion, or Tiamat, you see the value of the materials which are inside the cells are rather low, the lowest even for Prussian white system. So if you then think about the recycling of systems, then maybe for NMC, the recycler is quite happy because if he recycles such a battery system, then he has in the end a lot of value in his hands and can sell the different components. For LFP is already challenging, but for the other systems, they really have to think how they can recycle such a technology in an efficient manner that you, on one side, of course, it should be also cost efficient, but also that you have some positive impacts regarding environmental issues. And therefore, yeah, if you think about the recycling independently from the process, if you now go for puro, hydro, or maybe some fancy direct recycling process, if you consider low value of materials, and then you really have to think about design for recycling, and that is not only then focused on the cell, that what I talked about, but then also of the module level and pack level. And that is, of course, totally conflicting with the present developments for electric vehicles, because they have now the tendency to go to cell to pack. That means a really intensive use of the volume for the battery, and then to make it really easy and stable, whatever, they use foam and glue to put everything together. And then, of course, that's really, really difficult for recycling. So in the moment, we have on one side the wish to improve recyclability, also especially from the government. On the other side, in the technology development from the different OEMs, we see a lot of going to cell to pack, and you use foam glues. Of course, maybe they have now to develop also then some ideas how to dissolve foam, to dissolve glue, but the recycling process is then even more complicated. So yeah, my message, please include also design for recycling methods and ideas. Then in the end, in 15, 20 years, there's also a good way to recycling the batteries, and especially which is true for all batteries, but especially true for low value batteries like LFP or even more for sodium. Yeah, that's from my side. I thank you for your attention. And now it's, of course, time for some questions. Thank you.
Okay, we have a few questions in the chat. First question is, okay, yes, the first question is whether the slides would be available, the PPT slides.
Yeah. For internal use, I can provide it, but so I will always say, please do not spread it outside of StoRIES. Yeah, within StoRIES, it's fine, but do not spread it outside of StoRIES. So I will provide a PDF, and maybe then, Fatima, you can provide this via StoRIES.
Yes, exactly. And
Excellent.
then we have another question in the chat. I've just sent it across. The question is, do you have any information on the type of electricity currently used by majors?
So that is, of course, that is an interesting point. Thanks for this question, because on one side, there's on one side the idea that if you put, for instance, just on the side of your production plant of battery cells, photovoltaic, and then, of course, you use the energy from the photovoltaic and could maybe manage a certain fraction of the energy, and the rest is only coming from the grid. Yeah? And then with such things, at least from the LCA point of view, you improve your energy grid mix because you have a high fraction of own renewables, maybe even then also with a better connected with a battery, yeah, to have then the compensation of the fluctuation provision of energy. And on the other side, maybe only a smaller fraction than just from the grid. Then is from the LCA side really good. But on the political level, in the moment, they on EU side try to say, okay, for all this, for instance, for this CO2 regulation and the calculation of the official CO2 footprint, it's not important for the government which energy you use directly in your company, sondern they consider the energy mix of the country or the region. And that is a little bit conflicting, yeah, because that is rather a political decision that they say, because that's the big hope. They say, okay, Europe has a good energy mix and hope they improve it further. And then, of course, this is an advantage for Europe. And then maybe it could be a disadvantage for others which have a not so good energy mix. And then for some was the idea, okay, maybe we go to a country with a bad electricity mix, but then we have at least on the side our own photovoltaic. But this will be from the political decision not accepted. Yeah, that means for this official CO2 calculations, they are rather with their thoughts towards, okay, we consider then the regional energy mix and not the specific situation of the company. That is yeah, still not fixed, but that is, of course, this kind of thoughts. That means we have a little bit of conflict between what we are normally doing with LCA. With LCA, of course, if somebody has his own photovoltaics or wind farm, why not? Yeah, then we include that. That's the academic perspective, and that's fair enough. On the political side, they go a little bit a different direction. I hope this answered the question.
Great. Just waiting for some participants typing in the chat. We have a question from Sabrina. You mentioned your different publications on LCA on emerging batteries. Could you explain what your different approach to conduct a normal and prospective LCA is? How do you include the perspective in LCA?
Okay. Also good question, because there was just a few weeks ago a workshop in our institute ITAS, together with some colleagues from Chalmers University, but also colleagues from Jülich and DLR Stuttgart and DLR Oldenburg, exactly on the topic of prospective LCA, because there are sometimes a different understanding, and there are even now, especially Chalmers University, which try to influence the community with their wording. Yeah. So because we have a rather long-term record, we always said perspective in the past, if we have a technology low TRL and we try to estimate what they then how they would perform in a higher TRL to have rather industrial production. That is then we always call this prospective, which now other people say that's ex ante. Yeah? And then, of course, if you then also say, okay, this is then the technology if they are produced today, but you could also say, okay, let's produce this technology, which is not ready for market. Let's produce that in 10, 20, or 30 years. And then what are the effects? And not only the energy grid mix, but of course that also the energy mix, which is behind the materials, has to change. And for that is then nowadays the way that you use dynamic database, and then you can then in this database you include energy scenarios, for instance, and then you can really exchange all the pre-chains of the materials and the energy year by year. Yeah? We did it in the past 10 years or 15 years ago. We did then a time resolved LCA, and then we only do it for some years. Then we say, oh, let's produce this technology 2030 or 2040 or 2050. Yeah, and then, but of course not with the idea or not the possibility to change the pre-chain of the materials. But nowadays with this dynamic database, then even all the pre-chains are changed, and then you really has a very good resolution over time. And then if you have the right research question, it makes sense to also conduct this. As I would say that's then the other called this perspective. I would say that's scenario-based prospective LCA, yeah, scenario-based. And so that's the thing. So even the community, they use different wordings and yeah, but in the end, we talk about the same. And yeah, so that is the development. So yeah, that means on one side, higher TRL level is already prospective or ex ante, or then if you include then we will produce it in the future or use it in the future. This is then with dynamic database, LCA database possible. Hope this answered the question. Okay, then there's a question from Saskia. Okay. Yeah, direct recycling. Yeah, that's a good question. Yeah, because that is a big hope of the whole recycling community. And I was just a few weeks before I was on the AABC conference in Mainz, an international conference, and they have their own session on recycling. And there was also, again, a few companies which I already know, which promised to doing direct recycling. And the idea is behind then yeah, to keep the value on a high level and bring it back directly to the usage. And that is even ongoing research activities on EU level. There are different recycling projects on EU level. We are also involved in one. It's called Renovate. I did not show any slides on that. Sorry about that. But the project is called Renovate. And also here, the direct recycling process is one of the major goals, because the idea is behind, of course, if I have low values in like LFP or maybe even sodium, I need to think about in a different way, and maybe direct recycling is at least part of the solution to have less efforts for the recycling process and bring it back directly to the reuse in batteries. We will see for production scrap. It's more easy for production scrap. It's more easy because it's then not aged, it's not used, maybe not even sometimes even not in contact with the electrolyte. So this way it's very easy. For the used batteries, yeah, which are aged and maybe even treated already thermally and so on. It's an ongoing research project, but of course there are already some small companies and also some bigger companies who say we are close to that and we reach really high recycling rates and so on. So again, that is the thing. There are small or bigger companies which saying, "Oh, we solved it already." If you talk with the direct people which doing the research and are really at the forefront of the research for maybe fraud flotation and such things which are quite important. For fraud flotation, it's quite important to separate the graphite from the rest of the black mass. That's still complicated and not easy, and yeah, but the other companies then, because they are also interested to convince, of course, investors and looking for risk money, they of course promise a lot, and sometimes it's not clear if they already managed now and solved the big points, or they still in a world of big promise. Yeah, you never know. Very similar to the Aqueon battery. Yeah, as I told the story. Yeah, you never know if it's now really true or it's just a promise or promise in the future. Yeah.
Okay, we have
Yeah, then yeah, from Dilshan. Yeah, Dilshan, very good. So wait, avoidance of raw materials coming from mines. Yeah, of course, when recycling, because if we recycle something, shouldn't it also increase the impacts due to the process? Yeah, of course. Yeah, the thing is, if you replace then the raw materials with a pre-chain, the hope is then the environmental impact is lower than the primary one. And as I showed, sometimes it's not true, yeah, because sometimes you would even increase, because then the impact of the recycled materials are even higher. So especially if you would try to recycle, for instance, the black mass. Yeah, the black mass is, if especially in different qualities. If you have a good quality of black mass, maybe it's easy. But sometimes you have a bad quality of black mass due to the pre-chain of the black mass, and then it's really difficult to recycle. Yeah. Yeah. So it's recycling. Yeah, the people always thinks recycling is the only way to go, and it's really good for society, but they totally forget that a lot of recycling processes are subsidized by society. Yeah? And that is true for a lot of things. Yeah? Even on the economic side, if a recycling process is subsidized, for instance, yeah, glass, for instance, or whatever, that means if such things are subsidized, it's already paid by society, and then you can do it in an economic way, because there's money in the system. But necessarily you have to check by LCA if it's really also good for the environment. It's not always clear. Yeah, and so you always have to check carefully if the secondary raw materials has really a lower impact than the primary ones. Yeah, because it's sometimes true, but maybe sometimes not. You have to check it in detail. Yeah. Okay.
I think we have
I
one
try.
more question from Dirk
Yeah,
Comrick.
Dirk. Yeah, but I have to check it in carefully. It's a relevant issue, of course, depending on scaling questions. So it sounds for me, if I understand correctly, there maybe if there are niche applications of batteries, if this is the question, and yeah, wearables, health tech, like active, including HPC, energy requirements, notebook, data center. Is there a relevant issue of common and LCR? Okay. Of course, there are always niche applications of batteries, and then sometimes the industry sometimes rather interested, yeah, to understand what that means, yeah. But of course, from a societal perspective, if there's a small niche application of a battery, yeah, it's of course, nevertheless, there's the battery directive, and everybody has to keep all in focus with the battery directive, yeah, which is rather new. So you have to follow, in any case, the battery directive. From a societal perspective, of course, it's not as relevant, yeah, because maybe you have a small niche application, and maybe then even if this works not well, it's not a big thing, yeah. But nevertheless, the industry is interested to better understand maybe how they could improve then maybe their collecting is a big problem of batteries. Yeah, that is a big issue. How to improve the collecting phase and do it that in an efficient way. And then also, yeah, how we can increase the recycling, and or maybe at least that their technology is not disturbing other recycling. It would be, for instance, recycler quite often, if they have a mixed quality of batteries, a different charge, and not only one source of the battery. And in the moment, the EU is heading towards a labeling of the battery. With a labeling of the battery on the cell, you can easily identify different cells, and you can then select the different batteries, and then you have maybe different battery types, maybe old-fashioned ones, and maybe with high nickel and cobalt content and no nickel and cobalt content, or maybe LFP separate, and then you can optimize your recycling process regarding your specific technology. If you have a mixed fraction, then it's really difficult, yeah, because there could be even some old-fashioned cadmium battery, yeah, accidentally, and you have to ensure that this battery not enters the recycling chain, such a battery with cadmium, because they would destroy your whole charge. And so therefore you have to ensure such things. Yeah? So EU-wise, we're heading towards labeling. It's quite important, because most important is that we can identify what is the battery type to develop high efficient, high specific recycling pathway, because you cannot treat LFP in the same way than NMC. Yeah? And therefore, yeah, that's the way to go. Any other question? I cannot see any other question. Sabrina schreibt, okay, looking forward.
I think that's it. Yeah, we don't have any more questions.
But Sabrina is still writing something. Maybe then we wait for Sabrina.
Oh, yeah.
Yeah.
Question.
Yeah. Okay, yeah, Econvent is of course always a database to use it. For this perspective, maybe you can just send me an email, and then I will just explain it personally to you, what is the way for Perspective LCA, and maybe also connect you with somebody of my group. Yeah, maybe that's the best way. Okay, excellent. Yeah, you'll find me easily in the internet, just with my name. Okay, then if there's no further question.
Yes, thank you very much, Marcel, for your interesting seminar. The seminar will be disseminated across on the StoRIES YouTube channel, and the slides will be shared within the StoRIES network, as mentioned previously. And yes, that is the end of the seminar. Thank you very much for your interesting presentation.
Okay, thank you. And yeah, if you have any questions, send me email. Thanks a lot, and all the best. Thank you.
Thank you very much. Bye-bye. Bye.
Bye.
Bye-bye.